Okay, this is board number 4, circuits 400 to 410. And I've gone ahead and built the whole thing, since at this point I'm hoping you guys are pretty savvy about building the circuits and understanding the process. Um, the board is about measuring voltage, and up until this point, we've um, practiced with the ohm meter, and we've measured resistance in series, and we've measured resistance in parallel, and I've kind of hinted about amperage a little bit. We're showing you how the amp meter worked. And part of this is that once you get comfortable with it all you can go back and do previous cards again or create your own circuits. And hopefully if you find yourself with questions, you'll be able to create an experiment that will answer them for you, or you can contact me and I'll try to lead you through it. Um, the, uh, the voltmeter is, in my opinion, the best diagnostic tool there is. So knowing how to read it is really, really critical. And I'll show you that, or I'll show you everything I know about it, and then you can try to apply it. The primary reason, there are several reasons, but the primary reason that it's the best tool is because the voltmeter is completely passive. There's no uh, there's no there's no danger of doing anything with it that's going to hurt anything, because the voltmeter has incredibly high resistance, and there's no current flow through it to speak of, which can be a bad thing when it comes to diagnostics, which we'll talk about. But the reality is that the voltmeter is going to give you the most amount of information with the least amount of effort, and that information, if you read the meter properly, cannot be misinterpreted, because the voltmeter readings are very specific and they're legitimate, and once you learn them, they'll direct you to a fault if you have a fault, if you're working on this stuff. And my assumption, of course, is that either you are or will be working on equipment, machinery, or whatever, and that's why you're doing these cards. So that's how I talk about it. So we'll talk about measuring voltage, and then we're going to do some experiments down here so that you can practice. And the point of this, obviously, is to experiment and play around and ask yourself, well, what would happen if I did this, and to do it. And if you burn out a couple of solder fuses, so what? That's why they're there. So let me zoom in here and get started. Okay, the first thing is I want to point out the notes here. Voltage is pressure. I know some people find fault with that when I say that, but that's how the books say it, and quite frankly, it's the best mechanical analogy that I can think of, because voltage technically can be pressurized. And for those of you who are teaching, if you teach this, let me point out that air, in my opinion, is a better example, because air can be pressurized and fluids cannot. And most 18-year-old kids have never had a hydraulics class, but they have put air in a tire. So if you're going to be teaching these subjects, or this subject and these concepts, I would work towards using a balloon or an air bottle or a shop pressure or something to explain voltage instead of fluids, because pumps and hydraulics do not provide pressure, they provide flow. And in my case, if I teach somebody who knows that, and I say it, and I make the statement that a pump is like a battery because the battery's pressure, then everybody immediately loses faith in me, and my credibility is shot. So I don't do that. So the voltmeter is a pressure gauge, so you're actually reading a differential pressure. So when you read the difference between this point and this point, for example, and notice how I have voltage, voltage drop, voltage, voltage, voltage drop, voltage, and I'll explain that. But if you're going to read voltage here, what's happening is that the meter is looking at the difference between the red lead and the black lead. This is your red lead, because can't black and white, it can't be red, but that's the red lead. So the red lead and the black lead. So in this case, the reason it's reading 12 is because this is 12 and this is 0. And 12 minus 0 equals 12. Okay? Now, that's with the switch open and with the switch closed. Okay, so that's open and closed. So this is open, and you read full voltage across the open, which, by the way, is in series with the circuit. So I don't particularly like saying voltmeters are connected in series and parallel. I don't like that. To me, it's confusing. So with the switch open, I'm reading 12, but with the switch closed, I hope to read pretty much 0, because if the switch is closed, it's going to be 12 on this side and 12 on this side. So 12 minus 12 is 0. With it open, it's 12 minus 0 because it's touching ground. So until we close the switch, this wire and the light are touching ground, and they're technically part of ground. So with the switch open, here I'll read 0 because I've got 0 here and 0 here, and 0 minus 0 is 0. Okay? So this is with the circuit off, and this is with the circuit on. Same here. If this switch is open, this is connected to ground, so that's 0 here. It's connected to ground at 0 here. 0 minus 0 is 0. Here, this is a voltage drop reading because it's across. With the light switch off and the light off, you have 0 on this side and 0 on this side, so 0 minus 0 is 0. And in this case, on or off, this is touching ground and this is touching ground, and that never changes, so this is 0, this is 0, 0 minus 0 is 0, or if it's working, everything on ground should be 0 volts. You want it's going to be millivolts, it's going to probably be millivolts, okay, but still, practically 0, and that's just easier to write. So in the first case with the switch open, this part is voltage, this part is ground. But with the switch closed, this part is voltage, and this part is ground. And what happens is the light consumes the energy. So if the light is using it all up, it comes in at 12, comes out at 0. 12 minus 0 is 12. So that's why we get a voltage drop. We'll do that down here. Now, it says here there are two ways to read voltage, either voltage or voltage drop. That's my way of saying it. Voltage is just relative to ground. So anytime you put the black lead on ground, you are technically more or less reading voltage. If you put the voltmeter across a component, across a switch, or across a light, you're doing it because you expect a different answer. You're looking for what the energy being used by the component is. So in this case, we don't want the switch to use anything up because that would be bad. If we drop voltage here, the light would be dim, right? Corrosion, resistance, more resistance, dim light. So that's a bad thing. So we don't want to lose voltage in the switch in the form of heat. We want to see 0 loss. So there would be, that's 0 loss. And when it's over the light, we do want the light bulb to use up 100%. So we want it to come in at 12 and come out at 0. In at 12, down at 0. So with the voltage drop, when the circuit's on, we want to see 12 volts. And that's the biggest problem with voltage reading, is people don't know the difference between these two readings. And the easiest way that I know of to explain it is to say that if you put the black lead on ground and you probe the circuit, you're reading voltage. Okay? If you put the red and black lead across a component, could even be the wire, but if you're putting it across something, you're measuring voltage drop. So voltage is measured relative to ground with the black probe on ground, and that's just the easiest way to remember it as far as I'm concerned. So if anywhere you see anything that says voltage, read voltage, then they're expecting the black lead to be to ground. Voltage drop is measured across a device or load, and that's the key word, across. This is a measurement of the energy the component is using. In other words, if this bulb is using up 12 volts, I want to read 12 volts across it. Across it. The red probe is on the positive side, and the black load is on the negative side. The black circuit probe is on the negative side. So, by definition, if you are reading voltage, you are reading voltage relative to ground. If you are reading voltage drop, you are reading the energy used by a component, so your leads are going to be on one side of the component and the other. That's the difference. Okay, that's the difference between these two readings. Some people would disagree. That's fine. Whatever. Okay, but in my experience, this is the best way to keep the two voltage readings separate. So there's a detail on that, and there's the explanation for that. So if we were to turn the circuit off, then these would be our readings. Okay? Good grief. Can't do this. Okay, there we go. So if the circuit is off, then I'm going to read 12 volts coming out of the fuse. And then I'm going to read 12 volts coming into the switch. But if the switch is open, then this wire is touching ground, so I'm going to read voltage of 0 here, 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 and here. And if I read the voltage drop across the switch, I should read system voltage because this wire is at 12 and this wire is at 0. 12 minus 0 is 12. But if I read the voltage drop across here, then I get 0 minus 0 is 0. So I get no energy, and that's important. That's an important reading. Okay, then if I'm going to read voltage with the switch on, then I'll read 12 volts here just like the previous time. The voltage drop, I don't want this switch to use anything up, so it should read 0. And it's 12 minus 12, because as soon as you close the switch, 12 goes. All right, so I got 12 here, 12 here. 12 minus 12 is 0. Okay. Here I'm just reading the voltage coming out of the switch. It's 12. Here I'm reading the voltage on the wire, and that's 12, because this wire is voltage and this wire is ground. I'm reading the voltage drop, and that's reading 12, which is a good thing because 12 minus 0 equals 12. But when I'm on the ground side, this wire is at 0 and this wire is at 0. So I'm reading 0 minus 0 is 0. So I'll be reading 0. Now we'll do these down here and we'll show you. Okay, so that is that. I'll zoom back out. Okay, now I'm set up to read voltage on the circuit that I've built here. All right, and this circuit are identical. And the other thing you need to know is that these two circuits and this circuit, no, not that circuit, sorry. This circuit and this circuit are essentially the exact same circuit that you're going to see every single time you read a schematic and draw a circuit. This is what you're going to see. And when I tell people to redraw the circuit, I say draw a straight line across, put your voltage on one side, put your ground on the other, and that drawing is 50% complete. Put a load in the circuit somewhere, and that's 75% complete. So the only thing missing would be the switches. So power, ground, load, and switch or switches are the only things that you're looking for in the circuit when you're initially trying to understand how it works. Okay, so let's do the pretty much exact same measurements here as we did here, and let's see if it confirms it. So the first one is coming out of the fuse to ground. Okay, and sure enough, I expected to read 12, and I'm reading battery voltage 12.9. And the next one was to ground and coming into the switch, and sure enough, I've got battery voltage coming into the switch. Now the switch is off because the light's off. See, light works, so I'm turning the switch off. Now I'm going to go from ground coming out of the switch, and notice I've got 0. Okay, and that 0 is because the voltage at both probes is 0, and 0 minus 0 is 0. All right, then I do it just somewhere in the middle of the circuit. And this is one of the advantages of this copper tape, is you can measure pretty much anywhere. Again, I got 0. 0, 0, 0 because it's 0 minus 0. There's 0 here because the switch is open. And if the switch is open, then this wire is touching ground. So this wire is touching ground, and this wire is touching ground. And 0 minus 0 is 0. Okay, then it says a voltage drop across the light. So I'll put it on both sides of the light. Well, once again, I have 0 on this side and 0 on this side. So 0 minus 0 is 0. And then if I go on the ground of the light to ground, then I'm also reading 0. Okay? Because 0 minus 0 is 0. The meter is reading the differential pressure, okay, between the two leads. Okay? Which brings me to 2 voltage readings you must understand, and the reason that I recommend an auto ranging meter. It's kind of hard to see where it says auto right there. Auto ranging meter, okay, because you get better results. This reading right here, where the 2 leads are not touching, and if you kind of wave the leads around a little bit, you get this fluctuating voltage right here. Refer to that as ghost voltage. And if you have a ghost voltage reading while you're looking for voltage, then it means you have an open. Okay, so the leads aren't touching. But if you do have, if you have a short to ground, there's 3 faults: open, short to ground, high resistance. If you have an open, you get the ghost voltage, but if you have a short to ground, you get 0. Now you can do this all day long, and it stays 0. Okay? So ghost voltage means you have an open. Just trust me, man. 13 years later, it still works. And I'm telling you to read voltage. And if you get 0, then that means you have a short to ground. And that's pretty absolute. You cannot doubt that if you read the meter properly, and your meter can give it to you. All right, well, let's do the second set. Okay, the light bulb's on. So now we're expecting 12 volts coming out of the fuse. And sure enough, we get just slightly less than the 12.9 because the battery's going to lose a little bit. And then we do a voltage drop, and we want the voltage drop across the switch to be pretty close to 0, which it is. If this number had been any higher, then that would have meant that the switch was corroded. And if the switch was corroded, then you would have had a number here. But because the number is 0, that means the switch is not using any energy, because I'm measuring the voltage drop across the switch, which measures energy consumption, and this switch is not consuming much energy at all. That's a good thing. Okay. Now if I do this test where I read the ground, I should have system voltage because it's coming out through the switch. If I do it here in the middle somewhere, it's the same exact idea. Okay, notice the battery's tapering off there. That's normal. All right, but now I'm going to read the voltage drop across the bulb, which is the only thing in the circuit that should be using energy. And what's happening is the bulb is turning voltage into light. So if I read across here, I'm getting full system voltage. Now, just to prove a point, watch what happens when I turn it off. Remember, it was on a minute ago, off a minute ago. Now I'll turn it back off, and it goes to 0 because the bulb's not using any energy. But in this case, the bulb is using, not only is it using energy, it's using all the energy because this is the number we expect to see. And that's voltage drop. Then I make the measurement coming out on the ground, and I get pretty close to 0, right? And there's a little bit of a drop. It was 0, but now it's a little bit higher because there's current flow, and even this copper foil has resistance. So it's pretty close to 0, and that's the number we expect. Voltage on ground would be evil. If we had voltage on this ground, that would be bad. Okay? So that confirms that these readings are correct. And